Hi guys, good morning. So there are three of you. I'll just wait for 2 more minutes. Let people join. So guys, which chapter is going on in your school? Any idea? Hmm? Which chapter is going on in your school? Hi guys there. Hello. Guys, hope you're able to hear me. I can see the three of you. Rahul, Anisha, and Rohan. Are you guys there?
Sir,
Okay. Fine. So maybe if it's your background is too noisy, maybe you can put it in the chat box. Which chapter is going on?
What did you ask?
I asked which chapter is going on in your school. Like what chapter? How much they've completed?
They're teaching hydrocarbons. In
Hydrocarbon.
volume
Okay.
1, they
Hmm.
have states of matter and equilibrium left. They finished thermodynamics.
They finished thermodynamics.
Yes, sir.
Oh, okay. So
I
maybe
think we
after.
have 4 lessons left in school.
Okay, okay. So I'll finish this equilibrium. Then we'll go for general organic chemistry and hydrocarbons, and that's it. We are done. What else? Is S&P block is left. Yeah. So
Yes, sir.
S&P block will plan like a quiz, right? So because it's a full theoretical chapter, right? So I'll ask you to study a topic and come, right? And we'll be having a quiz. Maybe depending on the strength, we can have groups or we can have individuals, right? It depends. So
So
we'll
if
see.
possible, can you
Hmm.
even do something for hydrogen? It's
Hydrogen.
there it's in, sir, for example.
No issues, no issues. Same thing. Like what we do for S&P block, we can do the same thing for hydrogen because both are similar chapters. Full theoretical. There's no logic, not like no logic, but still, like majority would be just to remember rather than to apply logic there, right?
Okay, sir.
Okay, yeah. So now four of you. Okay, fine. I think we can start, or we'll wait for just 1 more minute. So the exams which you wrote, that half-yearly exams, like which we had a holiday for.
Not sure, sir, what you call it. It's only an online assessment, they told. But it was
Okay.
for 70 marks.
70 marks. Okay. Then it should be basically an half-yearly exam. Like at least they won't call it that way. Right. Okay. Fine, guys. We'll start. Let me share my screen. So, guys, hope you remember what we saw last class. We just were doing a lot of problems, right? And I told you how to do the approach and stuff, right? So maybe we'll just do one more problem and then we'll continue. One second, give me a moment. Okay. Take it on this question, people. Right. The question is for the reaction of this 2SO2 plus O2 gives 2SO3 for this reaction, right? They tell that Kp for this reaction is 4.0, right? Right. Okay. So that is right. For the reaction, Kp is 4.0. Okay. Now continue. When equilibrium is reached, mole fractions of SO2 and SO3 are equal. Mole fractions of SO3 and SO2 are equal. Right. Now the question is, find the partial pressure of O2 at equilibrium. Find the partial pressure of O2 at equilibrium, right? So the question is, they have given you a reaction, they have given you the Kp value for that, and they tell that at when equilibrium is attained, the mole fractions of SO2 and SO3 are same, right? Now they're asking, at equilibrium, what is the partial pressure of O2? Right. So maybe I'll give you 2 minutes. Just think about it. Now, just now we saw how to incorporate your mole fractions and how do you use your partial pressures, total pressures, mole fractions, connect them, and then use the Kp equation. We did all that. So similar problem we did just the last problem we did last class, right? Just try to apply it. And as I'll do it, I'll give you 2 minutes. Go for it. Hope everybody's trying. Don't sit idle, please. Okay. Any answers? Or at least did you get the approach?
I got till mole fraction x is equal to 1/2. I got, sir.
Okay, fine. We'll see what is that. Cool. Fine. So let me start with this. Okay, guys, they didn't give you anything about the number of moles, the initial number of moles they have not given, right? So here the table is not going to be much help for us, right? I mean, the equilibrium table is not going to be much helpful because they didn't give us the initial number of moles of SO2 and O2. right? So we have to do this problem a little differently. We'll see how we can do this. Okay, right, fine. So now let me directly take the Kp equation, right? So how will I write the Kp equation here? Kp will be equal to partial pressure of SO3 squared divided by partial pressure of SO2 squared into a partial pressure of O2. That's it. Okay, right. Now I think this is going to be a very easy problem, I guess, isn't it? Okay, we'll check. Right. So now if I convert that into mole fraction, right? If I convert every partial pressure here in terms of mole fraction, right? And mole fraction in total pressure, right? Say now this is going to be equal to total pressure into the mole fraction of SO3 whole square divided by total pressure into partial pressure of SO2 the whole squared into total pressure into partial, this is X guys, okay, partial into partial pressure of O2. That's it, right? This is the equation for Kp, right? Now what they have told us in the question is the mole fractions of SO2 and SO3 are equal, right? So definitely I will be able to cancel Pt squared and Pt squared, and since they have given me the partial pressure of SO2 and SO3 are same, I can cancel this also, right? So what do I get? I get Kp that is equal to 4, which is equal to 1 divided by total pressure into mole fraction of O2, or I can even write it as 1 divided by partial pressure of O2. Isn't it? This P total into the mole fraction will give me, right? P total into mole fraction would give me partial pressure of O2. And that's what is asked in the question. So what is it? PO2 will be 1 divided by 4, which is basically going to be equal to 0.25. That's the answer. Right? I think everybody understood. Easy. Just formula substitution. Yeah.
Can we find X also, sir, in this?
In the sign, in the X,
like
X in the sign?
mole fraction X, like at T2.
If they have given, yes, if they have given the total pressure, right? If they're given this PT value, one second, this PT value, if they have given, yes, we'll be able to find the X value also. In the sense, the partial pressure of O2 can also be found out, right? But again, this can be found out, but if at all you want to find the percentage dissociation of the, I mean, how much a reaction has been completed and all that, you require the initial number of moles. They should say that, say 1 mole of SO2 and 2 moles of O2 are taken, something like that they should have told in the question. Then yes, we'll be able to find whatever we want to find. Okay.
Okay, sir.
Right. So in this question, it's just going to be formula substitution. It's pretty easy problem. Right. Okay. So that's it, people. Like, we will stop with the problems for now. Anyways, you have to do a lot of problems in the ionic equilibrium part. So fine. Cool. Right. So now we know what is equilibrium constant, different types of equilibrium constants, and we know how to do problems in that also. Right. Now, next thing what you're going to see is that I am going for connecting the previous chapter and with this chapter, that is connecting equilibrium with thermodynamics, right? So there are going to be certain thermodynamic quantities which can be connected to the equilibrium constant. Okay, now I'm going to give you an equation, like there is a derivation for this, but you don't have to know the derivation exactly. So the derivation is like this, right? So delta G, we know what is delta G, right? Delta G is my Gibbs free energy. Now this delta G is equal to, right? So delta G is equal to delta G naught plus RT ln QC. Now this equation we have to remember. And guys, don't worry how it came. It's not important for you, right? So this delta G is the non-standard Gibbs free energy. And I already told you, when I put a naught, that represents standard values, right? Standard in the sense, the conditions are temperature to be 25 degrees Celsius and pressure should be 1 atmosphere, right? At these conditions, if I measure some quantity, it is going to be called as standard value in the sense or standard Gibbs free energy, standard enthalpy, something like that, right? So this delta G, Gibbs free energy, is equal to delta G naught plus RT ln QC. We know what is QC, right? QC is going to be the reaction quotient, right? Now, if you don't want to use ln, we can even use log, but if you use log, the equation will little change. Delta G will be equal to delta G naught plus 2.303 RT log QC. Okay, now, okay, if you want to convert ln to log, right? If you want to do that, you have to multiply by 2.303. Okay, so there's too much mathematics involved. We'll not go into details of why we are doing it. Maybe you should have done it a lot of times in physics, maybe, right? So if you want this, basically the ln, if I say, it's basically going to be log to the base E. I think I already discussed a little bit about logs, right? There'll be the subscript value, that is, say I can write log A to the base B. Like that's how generally we write it, right? But we don't specify this particular base term because it's understood, because when I say ln, it's going to be log to the base E. But when I say generally log without saying anything, it is going to be log to the base 10. Okay. So anyways, if we want to convert this and this, I have to multiply by 2.303. That's what I did here. Okay. So this is what is, yeah.
So you told that there's some point you told why you're writing del G naught. When
exactly.
naught comes, what could you repeat that point?
Oh, so nothing. So I'm telling this overall enthalpy, and so not overall Gibbs free energy, that is non-standard, right, will be equal to the standard Gibbs free energy plus this term, right? So this is basically when the reaction is happening, right? So when the reaction is happening, obviously the QC will keep on changing and this delta G will keep on changing, but this is a constant value. Please remember that delta G naught is a constant value. Delta G can keep on changing. R and T should be same. QC again will keep on changing because, as the reaction proceeds, right? So the QC value will approach Kc. It will reach equilibrium, right? Okay, so this delta G is nothing. Delta G naught is nothing but standard Gibbs free energy is nothing. Okay, right. Now, when the reaction has reached equilibrium, guys, right? When the reaction has reached equilibrium, right? So what I have to understand is this delta G, the non-standard value, is no more going to be important. Okay, so again, this QC would have become equal to KC, right? So when I go to at equilibrium, right? At equilibrium, what happens? Delta G, this has no role to play, right? And I can write. I can just combine these two and write it like this. I have delta G naught is equal to minus RT, or if I can include 2.303 also, right? Minus 2.303 RT log of Kc. Now, this is more important equation than the previous equation. Compared to this equation is more important. Okay, so this is the equation connecting your equilibrium constant and your delta G. Delta G naught, to be very specific. Okay, so again, guys, you really don't have to know how this formula came, right? But if you're interested, you can obviously go through it. You can ask me how it came. But again, it's like there are a lot of other things to remember, like rather than remembering this. That's what I'm telling. Okay, so delta G naught is equal to minus 2.303 RT log of Kc. You have to remember this, right? And guys, if you can remember, when I talked about properties of equilibrium constant, right, I told you that you will be able to predict whether the reaction is spontaneous or not by looking at the Kc value. By looking at the equilibrium constant value, I'll be able to predict whether the reaction is spontaneous or not. And I told you, for a spontaneous reaction, K value, or say Kc value, should be greater than 1. Right? If you can remember, that's what I told you, right? And this actually comes from here, this equation, right? Because I know for a spontaneous reaction, delta G should be less than 0, right? So now if you do the calculations, you will get that Kc value should be greater than 1 for delta G to be less than 0. But again, if you can actually, what is that? Easily do it, right? So if I put delta G value as 0, right? What will be there? I have 2.303. Everything will come here again 0. So basically, I have log of Kc to be equal to 0. So what should be Kc value? Well, log of what is 0? Any idea? Log of what is 0?
Don't know, sir.
Okay, great. So please remember, guys, log of 1 is 0. Okay, log 1. Okay, I'll write it here. Okay. Log 1. Oh God, again, this problem is happening. Log 1 is 0. Please remember that. Okay, so obviously, if at all you want the log value, this value to be less than 0, you want the Kc value. This is minus. Please don't forget this is a minus sign, right? So you want the Kc value to be greater than 1. So anyways, please remember that for a spontaneous process, Kc value should be greater than 1. And where is it coming from? It is coming from this equation. Delta G naught is equal to minus 2.3 RT log of Kc. Okay, so this is about the thermodynamics of the equilibrium, right? So basically, you can even get questions from this. Okay, and you have to remember the R value should be 8.314. Don't forget, because again we are using energy here, right? Delta G is in terms of joules, right? So R value should be 8.314, and temperature should be in Kelvin. In Kc value, you can find out. Is it cool? Right? So it's a simple equation. You have to remember this. Questions might come. Okay, and we are not going to do any problems on that because it's going to be just formula substitution. Right? Okay, now we'll move on. Okay, now guys, okay, we have studied all the theoretical things. We've studied even all the practical problems, what we are going to face, how to do the numericals, everything we saw. Now the question is, guys, you have learned so much about equilibrium. The question is, say after the reaction has reached equilibrium, right? Is there any way to disturb the equilibrium? In the sense that the reaction has stopped. That means the reaction has reached equilibrium, right? So is there something which I can do which can make the reaction happen again? Like even after the equilibrium has reached, I will do to some external things. Obviously, we are going to do something. We are only the external factors, right? So because we are going to do something, the reaction is again going to start. Again, it is going to reach equilibrium. So hope you understand. Eventually, it is going to reach equilibrium. So I'm going to already reached equilibrium. I'm going to disturb it, right? And again, I'm going to make it reach some other equilibrium constant, or say equilibrium is reached. That's what you understand, right? So what you're trying to learn here is what are the ways in which I will be able to disturb the equilibrium, in the sense that what are the ways in which I'll be able to make the reaction happen again, either in the forward direction or the backward direction. Now, the second question is, if I disturb it, right? If I disturb the equilibrium, which side the reaction is going to happen? Whether it's going to happen in the forward direction or is it going to happen in the backward direction? So these two questions are the questions we are trying to answer in this particular area. Again, I repeat, how to disturb the equilibrium, right? Second, if I disturb the equilibrium, which side the reaction is going to happen? That is in the forward direction or in the backward direction? Well, like we are going to predict. Okay, now we don't have to do anything. There was already a scientist who helped us with this. Okay, so that guy gave a principle, right? So it is called Le Chatelier's principle. Okay, so this Le Chatelier's principle is going to help us basically decide which side the reaction is going to happen. But actually, you'll be able to use logic itself, right? I would prefer to use logic rather than this guy's principle. But still, when he gave a statement, it was a sensation at that time. At that point of time, the new research, all these things were very fascinating. Okay, so please take down the statement, guys, for Le Chatelier's principle. Okay, if there is an effect, if there is an effect which causes which causes or you can write which disturbs the equilibrium. Okay, if there is a effect which disturbs an equilibrium, the change in direction, the change in direction should be in such a way, should be in such a way that, should be in such a way that the effect, the effect is minimized, or effect is opposed, minimized bar opposed. Okay, I'll repeat the statement, right? If there is an effect, right? If there is an effect which disturbs an equilibrium, right? Comma, the change in direction is going to be in such a way that the effect is minimized. What you're talking about, the effect which caused the change in equilibrium. Okay, so the effect should be minimized or it is going to be opposed. Okay, now it's pretty simple. Let me give you an idea. For example, say you have a reaction that has reached equilibrium. Okay, now what you do is you add more amount of reactants to it. Okay, after the reaction has reached equilibrium, right? Now you are going to add more amount of reactants. Okay, so obviously now the effect which you're talking about, which is going to cause the disturbance in the equilibrium, is adding more amount of reactants. Again, I repeat, right? The effect which I'm talking about, we wrote something, an effect which causes change in equilibrium. The effect is here, in this case, is going to be adding more amount of reactants. Okay, right. Now, what Lich-Atlas has told is that there's definitely going to be change in the direction, either in the forward direction or in the backward direction, the reaction is going to happen. Right. Now, which direction is going to be depending on this effect, which I'm talking about, should be minimized in the sense that you added more amount of reactants. Okay, so the reaction is going to move in such a direction that the amount of reactants is going to get decreased. Okay, again I repeat, the effect you're talking about is increasing the amount of reactants. Okay, so according to Lich-Atlas, the reaction is going to move in a direction which opposes this effect, in the sense that you are increasing the concentration of reactants. The reaction is going to move in a direction where the concentration of reactants are decreased. Which direction? Which direction then? Which direction? If you want
Could
to
you repeat?
Okay, I'll start from again. Right, say I have a reaction like this. Reactants giving products. Okay, now it has reached equilibrium. Right, there's no change. Everything is fine. Nothing is changing. Right, now after reaching equilibrium, I am adding more amount of reactant. Okay, after reaching equilibrium, I am adding more amount of reactant. After the reaction is completed, now again I'm adding more amount of reactant. Right, now this is the effect. Right, adding more amount of reactants is the effect which is going to disturb this equilibrium. Is it not? It's a reverse reaction. Okay, so this is the effect which disturbs the equilibrium. Right, now what Lich-Atlas says is that now the reaction is going to get disturbed. It is going to move in the forward direction or in the backward direction, but what he says is that the direction of the movement, I mean, the direction of the reaction should be in such a way that this effect, that effect of increasing the reactants, should be minimized or opposed, in the sense that you are increasing the reactants, increasing the concentration of reactants, that is disturbing this equilibrium. So this equilibrium is going to move in such a way that the concentration of reactants are going to get decreased. The opposite effect should happen. That is that the reaction is going to move in such a way that the effect is minimized, in the sense that I don't want to see increase in the reactants. Right, so which side the reaction will go now? Forward or backward?
Go backward, right, sir? If reactants are increased.
See, if reactants are increased, okay, now what Lich-Atlas says is that the effect has to be opposed. That means I have to go in a direction where the concentration of reactants are decreasing. Then what I mean, which way? Forward or backward?
Forward, sir.
Okay, yeah, definitely forward, right? Because when I go more and more in the forward direction, reactant concentration decreases, product concentration increases, right? So hope you understand. If you look at if you study the statement again and apply this to this particular case which you took, you will be able to understand, right? Again, I repeat, right? So Lee Chatlis principle, if you look at the statement, it says that if there is an effect which causes change in the equilibrium, so we'll just pause it there, we'll come back. So we are saying there is a reaction, it has reached equilibrium. Now the effect which you're talking about is increasing the concentration of reactants after the reaction has reached equilibrium. Okay, now going back to this Ricciardia statement, right? If there is an effect which causes a change in equilibrium, the change in direction, in the sense that either going to be forward or backward, is going to be in such a way that the effect is opposed or the effect is minimized, in the sense that you are increasing the concentration of reactants. Now the reaction is going to happen. Which side the reaction is going to happen depends on which side I can decrease the concentration of the reactants, because the effect is increasing concentration. Now the change in direction should be in such a way that this is opposed. Which side will oppose? Basically, oppose means increase means decrease, decrease means increase, right? So you're increasing the concentration of reactants. Now I have to decrease it. So which side the reaction will go? Obviously forward direction. Now you guys, everybody understood what's happening here? Yes? No?
Understood, sir.
Okay, don't worry. Like we will prove this logically also, mathematically also, even if you don't understand now. Okay, so fine. So like as I told you, this is not going to be much helpful in all the cases. Like it is going to be helpful. Let me actually, when I look at the logical stuff, then I'll be able to correlate what happens here. So basically, what he's trying to tell you is that disturbing an equilibrium, it has to go back to equilibrium. So that's what it says. Anyways, so we'll move on. So what are all the ways by which I'll be able to disturb the equilibrium? One of them is this. Okay, so let me list out what are all the possible ways by which I'll be able to disturb an equilibrium. Okay, so first way, right? So first way is adding or removing reactants or products, right? See, a lot of things are connected here. You can add after the reaction has reached equilibrium, you can add more amount of reactant or you can add more amount of product, or you can, after the reaction has reached equilibrium, you can remove some amount of reactant from the equilibrium mixture, or say you can remove some amount of products from the equilibrium mixture. So four things are connected here, but you can see at once it's pretty simple. Okay, right. Now let me take a reaction. Say I have R giving P is the reaction. Reactants giving product is the reaction. Okay, now the reaction will have a Kc value. Is it not? Because it has reached equilibrium. Some value will be the Kc. Right. Now let me take a case. Okay, now say let me take the case which I took the last case. Say I'm going to increase the concentration of reactants. Okay, now if I increase the increase means I'm going to add more amount of reactants after the reaction has reached equilibrium. Okay, now it is not anymore at equilibrium, isn't it? So I will now Kc value is constant, right? But now since it's not at equilibrium, I'll be using my reaction quotient. Is it not? Only when the reaction is at equilibrium, I can use Kc. Now since I have added more reactants, now we cannot use Kc there. We'll have to use Qc because it is not at equilibrium anymore. Right, now how will I get Qc? Now Qc will be product concentration divided by reactants concentration. Okay, right. Now what I did here, basically this QC was equal to KC before, right? Before adding your reactants, this QC and KC have been same, right? But what I did now, I have actually increased the concentration of reactants. Is it not? Right? The concentration of reactants has to be increased. Okay, so if I compare QC and KC values, which will be greater, which will be lesser? Tell me. Which is greater, QC or QC or KC for this particular case?
Kc will be greater.
Obviously, right? Because you're increasing the denominator in the QC, right? So obviously, in this case, you can see that QC is less than KC, right? QC is less than KC. QC less than KC, which direction? Whenever you find this, QC less than KC, which direction? We told, right, when we can see three cases when I have QC and KC. One is when QC is equal to KC, that is at equilibrium. When QC is less than KC, there is one direction. QC greater than KC, another direction. So when I have QC less than KC, what is the direction of the reaction?
I think reaction will go forward, sir.
Yeah,
It'll go
again,
forward.
whenever you have confusions like this, like just again go. So I want to reach equilibrium. Okay, now I want to reach equilibrium means this QC has to reach KC, right? That then it has to become equal to KC, right? So what should I do? Now forget this is about a different case, but generally what will you do the QC? The product concentration has to be increased, the reactant concentration has to be decreased, isn't it? Right? Only then you will be able to increase the QC value. Is it not? This QC value has to be increased so that it becomes equal to KC. Correct, right? How will you generally do it? You can see that this is going to be product by reactants. The product concentration has to be increased and the reactant concentration has to be decreased. So obviously you will see that the reaction is going to move in the forward direction. Pretty simple. Now that's exactly what you got here. Okay. Right now, again, if you apply logic, you are adding more reactants. So the reaction is going to move in such a way that the reactant concentration is decreasing because the effect is increasing concentration. So the result should be such a way that the reactant concentration is decreasing. So obviously it has to go to the forward direction. Okay, now you can see mathematically also that's what is happening because now this Kc has been this, what is that? The equilibrium has been reached. So we have a Kc value, right? So from this equilibrium state, I am increasing the concentration of reactants. So it is not anymore Kc, it is going to be Qc, right? So that is equal to your product concentration by reactant concentration, and obviously you have increased the concentration of reactants. So if I compare this and this, QC will be less than KC, and if QC less than KC, you can easily understand that it is going to move in a forward direction. Okay, any questions, any doubts anywhere from this?
No, sir.
Okay, so like let me take some other thing, right? Say we have 4 cases here. You can apply all 4 cases, but I'll just do one more case, and rest 2 cases is pretty easy, right? You can do it by yourself. Okay. Say again, I have reactants giving products, right? I have this reaction. Say the reaction has reached equilibrium. Right, the reaction has reached equilibrium. Now say what I do is after the reaction has reached equilibrium, I am going to decrease the concentration of products. Okay, I am going to decrease the concentration of products. Okay, fine. Now tell me, now again, this reaction I will not be able to use Kc. I have to use Qc, right? So when I compare Qc and Kc, right? Now, which do you think will be greater? So again, this QC is basically going to be concentration of products divided by concentration of reactants. Okay, now what I'm doing, I am decreasing the concentration of products. Is it not? That's what I said here. I'm decreasing the concentration of products. Okay, now tell me KCQC, which is greater?
QC is greater this time, sir.
Obviously, right? So we are decreasing the numerator. So definitely this QC value will decrease. So definitely QC is less than KC. So again, forward direction. Is it not? Now we can see logically also, right? Now logically, now in the sense that we'll see Le-Chatelet's principle also. If I see, so the effect is basically a decrease in concentration of products. Okay, so the reaction has to move in a direction that this is going to be opposite, in the sense that it is going to move in a direction where the concentration of products are increasing. How will that happen? Definitely going in the forward direction. Only then more amount of products will be found and more product concentration can be increased. Right? So either by Le-Chatelet's principle or by using your QC and KC, we'll be able to prove what exactly is happening. Okay, right? So that is the first thing, that is addition. I mean, adding more reactants or adding more products, removing reactants, removing products. So all 4 things can be correlated here. right? So now even if you like, I think no, tell me now, when I remove the amount of reactants, okay, after the reaction has reached equilibrium, okay, now I'm going to decrease the amount of reactants. I'm going to remove some reactant from the equilibrium mixture. Which side the reaction will happen? Again, I'll tell you. So basically, again, I have this reaction, I have the Kc value. Now I'm going to remove some amount of reactants after the reaction has reached equilibrium. Which side the reaction will move?
Move backwards, sir.
Yeah, it is going to move backwards. So you can either see logically, right? So now I'm decreasing the concentration of reactants. That is the effect. So the result, that is the change in direction, should be in such a way that this reactant concentration is increasing. And how it will increase? Obviously, the only way is to move in the backward direction, right? Because more and more reactants will be formed. Now the reactants acts as product. Anyways, that is going to move in the backward direction. Okay, so like this, you'll be able to predict. Okay, so that is the first thing, that is addition or removal or of reactants or products, right? Now second case, how I will be able to disturb an equilibrium, right, is by change in volume. Change in volume in the sense, after the reaction has reached equilibrium, I am going to change the vessel, in the sense that I'm going to put it in a vessel which has more volume, or say I'm going to put it in a vessel where it has lesser volume, something like that. Okay, so obviously we know that all, say A, B, C, D for the reactants and products, they don't have different volumes. For all of them, the volumes are going to be the volume of the container, volume of the vessel only, right? So what I'm doing, after the reaction has reached equilibrium, I'm going to change the vessel, in the sense that I'm going to increase or decrease the volume of the container, right? Obviously, all the molarities and all these things will change, right? Now we'll see what happens to this kind of reactions. Okay, now guys, I'll be able to see this in two ways. Okay, one where I have delta N is equal to 0, and second case where I have delta N not equal to 0. Okay, now what do you mean by delta N is equal to 0? I think we already discussed, right? So when you have the total stoichiometric coefficient of reactants is equal to the total stoichiometric coefficient of products, for those reactions, delta N equal to be 0. I think we even took an example. So we'll take an example again. We'll see what happens. Say I have CO plus H2O gives CO2 plus H2. Right now, for this reaction, delta N is equal to 0 or not? Obviously, 1, 1, 2, again 1, 1, 2. So 2 minus 2 will become 0. Okay, now let me write the equilibrium constants in terms of the concentrations. We'll see what happens. Okay, now let me take a little bit, make some space. Okay, so if I write my Kp, sorry, not Kp, Kc, right? So if I write my Kc for this, how it will be concentration of CO2 into concentration of H2 divided by concentration of CO into concentration of H2O. Now you can ask me, sir, why are you putting H2O? H2O is a liquid, but here you can see all of them are gases, right? Temperature is very important, right? Now, obviously, this reaction will happen only when the temperature is about 150 degrees Celsius. And obviously, we know at 150 degrees Celsius, water will be in the form of water vapor. So I can include this. Generally, if it is in liquid form, what do I do? Liquid or solid, what do I do in the Kc equation? Do I include those in the Kc?
We don't include, sir.
What is the value which I have to put in place of them? What is the value for solids and pure liquids in the equilibrium constant equation? What is the value which I have to substitute?
1, sir.
1, right? So please remember that. I think we should have done problems on that. We will do it. Okay, so remember that whenever you have pure solids or pure liquids, the value should be 1. You don't have to substitute them in the equation. That's what you need to remember. Okay, so anyways, so coming back to this particular problem. Okay, so now we have the concentrations. Now let me do it in terms of number of moles. Okay, so now how will I write? It will be number of moles of CO2 divided by total volume of the vessel into number of moles of H2 divided by volume divided by number of moles of CO divided by volume into number of moles of H2O divided by volume. Okay, now what do you see here? All the volume terms are getting cancelled. I just have the number of moles, right? So what do you understand from this is that if for a reaction, if delta N is equal to 0, change in volume has no effect. This is what you need to understand. Why there's no effect? Because there is no volume term in the equilibrium equation, right? All the volume terms are getting cancelled. So whenever you see a reaction like this, whenever you see a reaction where delta N is equal to 0, change in volume is not going to have any effect, in the sense that even if we change the volume, the reaction is not going to proceed, in the sense that it will still be at equilibrium only. Okay, so again I repeat, when you have reactions where delta N is equal to 0, if you change the volume, there is no change in equilibrium. It is still going to be at equilibrium only. Okay, but when you have delta N not equal to 0, definitely there is going to be at least one volume term, right? So accordingly, the equilibrium is going to change definitely. Now we'll take some examples, right? So delta N not equal to 0 will take. So delta N not equal to 0 again can be delta N greater than 0, delta N less than 0, right? So let me take that. So delta N not equal to 0 again can be in two ways. That would be delta N greater than 0 and delta N less than 0. Right. Okay, now let me take a case for this and we'll see what happens, and we'll take a separate case for that and we'll see what happens. Right. Okay, so delta N greater than 0 means I should have more products than reactants. Anyways, we just do it. So say this reaction I can take, say PCl5, right, gives one second guys. Right, so PCl5 gives PCl3 plus Cl2. If I have this reaction, right, so you can see the total stoichiometric coefficient here is 2, here it is 1. So 2 minus 1, delta N is greater than 0, right? No issues. Okay, fine. So now directly, if I write my Kc equation for this, I'll directly write it in terms of number of moles and volume. Okay, so it will be number of moles of PCl3 by volume, number of moles of PCl3 by volume into number of moles of Cl2 by volume divided by number of moles of PCl5 by volume. Okay, this is what I have. Right. So one of the volume term gets cancelled. This and this gets cancelled. I still have one volume term. So obviously, if you change the volume, definitely the equilibrium is going to change. Okay. Now, say I assume that I'm going to increase the volume for this particular case, right? I'm going to increase the volume. So if I increase the volume, so this term will get decreased, right? Because I'm increasing the volume, right? This term will get decreased, right? So if this term decreases, what will happen to Kc? Kc will decrease because overall numerator is decreasing. So Kc value will decrease. So I can easily say that now Kc will not be equal to Kc, it will be equal to Qc. Now since Kc value is decreasing, Qc is less than Kc. Is it not? Because from this you are decreasing, and that decreased value is what is my Qc. So definitely Qc will be less than Kc. Again, I repeat, guys. So Kc equation is very simple. Number of moles of PCl3 by volume, number of moles of Cl2 by volume divided by reactants number of moles of PCl5 by volume. Okay, so one of the volume term gets cancelled. I still have one volume term left, right? So now assuming that I'm going to increase the volume, say if I increase the volume here, this overall term will get decreased. right? So if this overall term gets decreased, the equilibrium constant will get decreased. That means it will become equal to QC, and obviously QC will be less than KC. That indicates that it is going to be what? Forward direction. Okay, that is going to indicate that it is going to be forward direction. Okay, right. Now let me, any questions guys? It's pretty simple. I just substitute the values and I increase the volume and then seeing what is happening. Pure mathematics. Any questions? Okay, I hope you understood. Right.
So this
Let me
is
take
for
it.
del n greater than 0, sir.
See guys, don't worry. I'm telling you now. You really don't have to remember delta n greater than 0 if I increase the volume forward direction. No, you don't have to do that. I'm going to give you a shortcut after this. Okay, this is just for your understanding what exactly happens. Okay, but after all this, I will give you a shortcut that is going to be very very easy for you to remember. And I increase the volume, which side the reaction is going to happen. You don't have to remember all this, right? What you have to remember for sure is that you have to make sure that when I have delta n is equal to 0, change in volume has no effect. That's what you need to understand. And delta n not equal to 0 will have an effect, right? So anyways, we'll try to take another reaction, right? Delta n less than 0. Now you can easily see. So obviously you're going to get the opposite effect of what you're going to what you saw, right? And maybe let me take the equation. That is not a big deal, right? Say what equation I can take. Maybe I can take. Hmm, maybe if I can take the opposite reaction, but no, that is not good. Ammonia equation. Yeah, ammonia equation is the best equation. Yes. So I have N2 plus 3H2 giving 2 ammonia. So I can easily see here it is 2, here it is 4, that is 3 plus 1, right? So definitely delta N is less than 0, right? So again, I write my Kc equation directly in terms of number of moles. So number of moles of ammonia divided by volume squared, because there is 2 there, stoichiometric coefficient. This is H2 guys, right? Next, number of moles of N2 divided by volume, number of moles of H2 divided by volume cube, right? So what I have here, I don't care about the number of moles, just care about the volume. So this B, I have 1 by V squared, right, divided by 1 by V into 1 by V. Oh God. Okay, wait. Right, I'll just write it again. Right, so I can see from here, I just have a volume squared. Here I have volume power 1 and volume power 3 will become volume power 4. So basically I have 1 by V squared divided by 1 divided by V power 4, right? So if I bring this up, I basically will have V squared in the numerator. That's what you need to understand. In the numerator, Kc, I'll say Kc in this case will be equal in the sense that directly proportional to Kc. Or I can understand, right? This volume term will get cancelled. I'll get one volume term in the numerator. Last time I got the denominator. Okay, so now if I increase the volume, now obviously Kc will increase. Kc will, oh God, fine. Wait, guys. Right? Say, okay, so Kc will increase, and what will increase to? It will increase to Qc. So obviously you can see that Qc will be greater than Kc, right? So definitely this means that I'm going to have backward reaction happening. Okay, right. So anyways, you have seen how it actually works, right? Now let me give you the shortcut now. Right, now take it to the shortcut. Let me give you a statement. If you have taken this down, I'll give you the shortcut. What is the time? Okay, we have time. Right. For reaction, increase in volume, for reaction, comma, increase in volume will shift the direction will shift the direction of the reaction. Oh, we already wrote for reaction, increase in volume will shift the direction towards the side which has higher stoichiometric coefficient. Towards a side which has higher stoichiometric coefficient. I'll repeat the statement. For a reaction, increase in volume. See, we're not talking about just change in volume. We're specifying increase in volume will shift the direction towards the side which has more stoichiometric coefficient. Okay. Now, if you can realize this, we can go back to the previous example and you see what happens here. Now, you can see for this reaction, delta n, okay, for this reaction, what happened? When I increased the volume, we found that it is going to move in forward direction. Now look at the statement. We said that if I increase the volume, I am going to go in a direction where there is more stoichiometric coefficient. You can see the stoichiometric coefficient, total stoichiometric coefficient here is 2 and this side is just 1. So when I increase the volume, obviously I have to go to the forward direction, because in forward direction, the product side only I have more stoichiometric coefficient. Okay, now this is going to work here also, guys. Right, now we decided what? We decided that it is going to be backward reaction for this when I increase the volume, right? So now what happened? Now here you have 4, right? Here you have 4, here you have 2. So definitely it is going to move to a side where I have more stoichiometric coefficients. So definitely backward reaction. Okay, so you don't have to remember any of these. Whatever I did now, it is just for your understanding. But again, if they ask you prove it, then you can use whatever I used now. It's pretty simple. Okay, but generally they won't ask you like that. Prove that if I increase the volume, it is going to move in forward direction. No, that one they'll not ask you. This is just for your understanding, right? But what is the shortcut? If I increase the volume, the reaction direction is going to be in such a way that it is going to move towards a direction where I have more stoichiometric coefficients. Is that cool? Right? So Rohan, is that okay now? You don't have to remember anything. Is that fine?
Yes, sir. Could you just repeat the statement so I can check?
Yeah, sure. For a reaction, increase in volume will shift the direction towards the side which has more stoichiometric coefficients. Okay.
Okay, sir.
Right. Fine. So last, I'll just take 5 more minutes and I'll complete, guys. Right. Now we saw change in volume. Right. Now let me make a page. Right. Now we saw change in volume. So the third thing, first thing was addition, subtraction of reactants or products. Second thing was change in volume. Third one in our discussion is change in pressure. Right, change in pressure. Okay, now we don't have to spend much time on this. You can easily understand, guys. Pressure, according to Boyle's law, pressure and volume are inversely proportional. Okay, so whatever you saw for volume, the exact opposite is going to happen if you're going to increase the pressure. Okay, so please take down the statement. I'm going to give you the shortcut directly. Right, we don't have to prove anything here because we already proved for volume. So whatever happens for volume, that exact opposite happens for pressure. Right, so take down. Increase in pressure. Increase in pressure will shift the reaction. Increase in pressure will shift the reaction to a side which has lesser stoichiometric coefficients. Increase in pressure will shift the reaction to a side which has lesser stoichiometric coefficients. Okay, again, we're talking only about increase in pressure. Okay, if it is going to decrease in pressure, it is going to be opposite. Decrease in pressure will give me more stoichiometric coefficient. Same way, A decrease in volume will give me lesser stoichiometric coefficient. Anyways, you just have to remember any one of them, right? Say increase in volume, more stoichiometric coefficient, increase in pressure to a side where I have lesser stoichiometric coefficients. Okay, guys, right? Okay, pretty simple. So if I take an N2 plus 3H2 giving 2 ammonia, right? If I increase the pressure, it is going to move in the backward direction. Oh, sorry, forward direction, because I have 2 and 4 there, right? So exactly opposite of what we saw for volume. This thing is going to happen for pressure. Okay. Now I think there is 2 more factors which we'll see tomorrow, right? So the first part of equilibrium is over. That is, the normal equilibrium is over. After that, we can start with ionic equilibrium. Ionic equilibrium is little more. So here you saw more of theory. There will be full problems. Okay, ionic equilibrium. I think I'll be requiring some 3 classes for equilibrium, that is ionic equilibrium, and after that we'll start with organic. Right? Any questions, guys? Any doubts?
No, sir.
Right. What about others? Please give me a yes. There are almost how many people? I have 7 people here. Please give me a yes, everybody. Everybody understood everything. Okay, 2.
Yes, sir, understood.
Okay, 3.
Yes, sir.
4, 5.
Yes, sir.
6. One more. Okay, this one more is always a problem. Okay, if I want to find out, I can find out, but I'm really not interested in any of these. Okay, guys, thank you so much. We'll meet again. I think tomorrow we again have a class, right? Friday, right? So we'll finish the 2 more factors which are there. That is, would be a catalyst. If I include a catalyst, what will happen to the equilibrium? And second thing is when I have an inert gas getting added, right? Again, we'll see later. I mean, tomorrow we'll see, and we'll go for ionic equilibrium. Okay, thank you so much, people. We'll meet again.
Thank you, sir.
Thank you, sir.
Yeah.